P is less than or equal to the allowable. So we simply plug in the numbers 5/8 times P times R is 9.75, and thickness is 0.25, less than or equal to 10.510 times 10 to the 3 psi. So from here we should be able to calculate P. I don't have the numbers, so I just leave it here. Okay. We're good? Okay. Sometimes the pressure vessel will be used as the supporting material. For example, some people, I've seen that people kind of play sitting on the pressure tank. I don't know why, but they sit on there. Okay, so that means this is the tank. This is a pressure vessel. This is a tank, and this is welded, for example. So there's a two, for the example I just raised, there's a two types of the loading. One is the gauge pressure here inside. The other one is the big butt applied to the loading here. Okay, so from here that comes to the combined loading case. So for the distribution of the stress here, for this element, you expect is one is due to the pressure of the gas inside, and also due to the application of the P, you expect another additional P. Sorry, let me use F. So additional F over the area. The area is how much? For this one, the area will be equal to 2 pi R times T. So here is the cross-section viewpoint. So this is the R, and the thickness is T. So this is the area on which the force, the weight of the body applied. Because T is very small, so basically the area can be approximately equal to 2 pi RT. Or otherwise, if you want to be precise, you can do the calculation, but that should be good. So in this way, in this direction, you have to combine the two things together for your remaining calculation. Okay. So that is the combined loading, the scenario. Any questions so far? Should be straightforward. And then we have one more little topic in the evaluation.
So we have the F divided by 2 RT is the sigma as well, or?
Sigma.
Previously you had you wrote out the term F divided by 2 pi RT, and didn't set that equal to anything. What is that?
This area, right? So for example, this area, if we do the precise calculation.
Yes, I understand that area.
Okay.
You have the term.
So for this one, yeah. So in this way, this will be in this direction the total force.
Oh, okay. So that's applying to that picture as well.
Yes.
Okay, that's,
yeah. So yeah. Okay. And the very last topic is the spherical, and this one has less applications and compared to the cylindrical one. But this one, the same.
We're back.
Oh. So here again, we take up any stress element in any directions. So here we simply say, for example, if we want to find out the sigma 2, then simply we make a cut that expose a cross section in which sigma 2 take effective, like this. So in a similar way, we take the equilibrium equations, then we can calculate the sigma 1, the sigma 2 equal to Py over 2T. The same thing applies to sigma 1. And for spherical pressure vessel, that is very straightforward. the sigma 1 equal to sigma 2 equal to PR over 2T. Basically, this is a very typical, we call the isotropic design. Isotropic, that means the result or material properties is independent of the direction. We call it isotropic. And orthotropic, I think if you go to Home Depot to buy the laminate wood, then due to the structure of the wood, the texture of the wood, then you can feel the strength is different in direction. That's called orthotropic or anisotropic. Anyhow. So that result is pretty much straightforward. So for this case, I'm sorry making you so forward. Okay, so here we can try to draw the Morse circle. So for the Morse circle, here will be equal to, I can rewrite here. So that would be equal to PR over 2T. And the radius for this case will be equal to 0. So for this case, that is the first time we've seen the Morse circle actually is a point here. Okay, so this is a Morse circle. And that is equal to PR over 2T here. Okay, so basically for spherical pressure vessels, there's not much to say. And because everything shrinks to 1 point, everywhere you look at the same value in everywhere in each direction. So that is very straightforward. That's it. Thank you.